For this question, we're talking about permutations and combinations, and we're doing problem type 2. Here we're beyond just using the formulas. We really have to figure out which formula to use is kind of the hard part here, and they're going to intentionally mix these up. So I've chosen a version that has one permutation and one combination, but as you do these, it's very possible you're going to get both scenarios are permutations, or both scenarios are combinations, or you may have one of each. So as you look at these, and again, the key is understanding that with permutations, order matters. So with the permutations, the order matters. With combinations, order doesn't matter. I'm trying to write small, pardon my bad handwriting. And so that's the key to keeping them sorted out as you read these. So reading part A, it says, there are 12 European cities that Jenny would eventually like to visit on her next vacation, though she only has time to visit 4. One on Monday, one on Tuesday, one on Wednesday, and one on Thursday. She's now trying to make a schedule of which city she'll visit on which day. How many different schedules are possible? Assume that she will not visit a city more than once. So if she's not going to visit more than once, that's a clue that it's without replacement. So we can't possibly go back to the same city. But the question is, how many different schedules are possible? So it certainly would matter if you go to one city on one day and then another city on another day, and then you mix that up with a different option, and you could flip those around, and that'd be an example of another schedule. So in this scenario, the order definitely matters in terms of just planning how many different schedules are possible. And so this is an example of a permutation. You're just trying to figure out how many different schedules are possible. So what are we saying? There are 12 cities that we have to choose from, and we're only going to visit 4 of them. So we're choosing 4 out of 12. So because order matters, that is, come on, get the eraser to work, or I'll hit undo. There we go. That is 12 P4. And so we can bust out our calculator and figure out math probability option 2 and go with 12 there and 4 there and say there are 11,880 different schedules. 11,000, there we go, 880 different schedules that she could arrange. And again, the key there was understanding, reading that and understanding that the order that you visit those different cities does matter in terms of going this route first would be one schedule, or you could flip it around and you'd have a different schedule, but still could hit some of the same cities. So this part B says, from 13 albums released by a musician, the recording company wishes to release 10 in a box set. How many different box sets are possible? So when you read this, if these 10 albums are in a box set, it doesn't matter what order we list them, it's still the same box set. So this is an example where order doesn't matter. So since order doesn't matter, we're doing a combination. And so that's 13C10. And so we'll do that calculation, combination of 10 items chosen from 13. And so math probability option 3, and that was 13C10. And so we'd say there are 286 different box sets that are possible. 286 86. And I'll just scroll down and mention just a couple things about the ALEKS explanation for this one. They're just giving you, first of all, just a general definition of permutations and combinations. Excuse me. And they're emphasizing that the order doesn't matter for combinations and the order does matter for permutations. So that's just a general definition. And so you see there's the permutation there for part A and the combination there for part B. And again, as you do these, just pay attention to that subtle detail.